In this video, we'll go through questions 1 to 20 of the 2022 New South Wales HSC Chemistry Exam. This is my first pass at these questions and does not include any references at the end, as I have done in my previous videos for the 2021 exam. Hopefully, this is still a useful resource for you, but please leave any comments or questions below around this, or if you want me to clarify any of the exam questions further. So, on the first page we have questions 1 to 3. Let's start with question 1. It asks, what term is used to define the repeating unit of a polymer? To answer this question, it's just a matter of remembering that C, monomer, is the term used for the repeating unit. The rest of these are other chemistry terms. Dimer is a molecule made up of two monomers. An isomer is a variant or possible chemical structure based on a given chemical formula. So for example, we can have 1-propanol or 2-propanol, different structures but the same chemical formula, C3H7OH. That is, they are isomers. Lastly, a primer is a short segment of RNA that's used in DNA synthesis. Moving on to question 2, it asks, when a solution of a primary standard is prepared for titration, which of the following is required? Now the important point here is that it's asking about equipment needed to prepare for titration, not used in the titration itself. A primary standard is made beforehand, and to make it you need to have weighed out a precisely known mass of the substance itself. Therefore, to measure mass, we use a balance, and therefore option B is the answer. The other options can be eliminated as well. A burette is used in the titration process itself to measure volume. The indicator also used in titration to find the endpoint. And lastly, a condenser is used in liquid-liquid separations, not in titration. Question 3 asks, which of the following features is not a characteristic of a state of equilibrium? We can go through these one by one to eliminate which state is wrong. So equilibrium is indeed achieved in a closed system, as we need something where there is no matter or energy that's coming in or out of the system. That would disturb the equilibrium. Also, equilibrium does not depend on the temperature, and is the only factor that shifts the equilibrium point. Also, the equilibrium point can be reached from either direction. It is a reversible reaction in the end, and therefore can always be written with products or reactants on either side. Therefore, we know that option D is the answer, and indeed the equilibrium concentration of reactants and products need not be equal. Remembering the acronym PORC, we know that the equilibrium constant K is just the concentration of the products divided by the concentration of the reactants, both to the power of their stoichiometric ratio. If the concentrations were always equal, then K would always have to be 1. And we know that equilibrium constants can vary widely from very small to very large numbers. Just look at the data sheet at the back of the exam. The next page has a single question, question 4. This question asks, an analytical chemist was using atomic absorption spectroscopy to determine the manganese concentration in a sample. The following diagram shows the absorbance lines of manganese. This is followed by a spectrum between 380 and 750 nanometer wavelength, with the 4 absorbance lines for manganese clearly marked. The question continues, the diagrams below show the emission spectra of 4 AAS lamps. Which lamp should be used to determine the manganese concentration in the sample? We then have options A to D, taking up the rest of the page with the emission spectra for each. So with the AAS technique, to ensure maximum accuracy, we want to choose a lamp that is as close to possible to the target metal as possible. The emission lines should intersect with the absorption lines of the manganese. Then there is basically a one-to-one relationship between absorbance and the amount of metal in the sample, and the measure of light becomes a measure of concentration. So we basically want to match up the lines in the top spectrum to one of the ones below. Looking at all the possible options, we can see that option C is in fact completely overlapping. We can view this with the straight line tool, but in the exam you could use your ruler to align with the spectrum. Comparing all the options, it's clear that option C is the answer here. The next page has questions 5 and 6. Question 5 asks, which pair of ions can be distinguished using a flame test in the school laboratory? We can eliminate the options to see which is possible. Option D is just the same element in 2 ionic forms. This would produce the same spectrum. Option C is also not the answer, as flame tests are only run on metal ions. In option A, the silver ion cannot be tested via the flame test, similar to other low reactivity metals like gold and platinum. Therefore, option B is the answer, as it's the only one to have 2 metals that will produce visible colors in the flame test. Question 6 then states, a UV visible spectrometer was used to obtain the spectra of solutions of substances P and Q. The absorbance spectra are shown. We then have a spectrogram with 2 plots of the absorbance spectra. The question is, which wavelength would be appropriate to determine the concentration of Q in a mixture of the 2 solutions, followed by 4 options. First of all, in order to clearly distinguish Q, we want a spot where absorbance is high, but there is no interference from the other solution P. Solution Q has two absorbance peaks, here and here. This peak has overlap with solution P, even though it does have a higher absorbance peak. On the other hand, the other peak is lower in absorbance, but there is no overlap with solution P. This spectral region is closest to option D, 630 nanometers, and therefore this is the answer. Going on to question 7 on the next page, it asks, the name 2-ethyl-3-chlorohexane does not follow IUPAC conventions. What is the systematic name of this organic compound? The easiest way to answer this question is to draw out the structure of the compound implied by the name, and then just name it correctly. So we start with the 6 carbon atoms implied by the hexane, then add the ethyl and chloro groups to the second and third carbons. We can pretty quickly see why the name is wrong, as the longest carbon chain is actually 7 carbons long, meaning the prefix is hept. Labeling from this side, we see a carbon/methyl group off the third carbon and a chloro group coming off the fourth carbon. Therefore, option B is the answer. Although I haven't drawn out the hydrogens, if I did, this would be CH3 and therefore a methyl group. If we labeled from the other direction, the 2 groups would be off the 4th and 5th carbons, and therefore a higher number, which doesn't follow the IUPAC nomenclature. The next question, question 8, has a reversible reaction between sodium hydrogen carbonate and its products, and asks, what is the equilibrium expression for this system? Firstly, we remember the acronym PORC, that products over the reactants gives us K, the equilibrium expression. We also remember that no solids or liquids are included in an equilibrium expression, only gases and aqueous solutions. Looking back at the equation, we see that only CO2 and H2O are in the gaseous form. Each of these is also in a 1-to-1 stoichiometric ratio, and both are products. Therefore, the equilibrium expression is just the concentration of each multiplied by each other. The next page has question 9. It has 4 structural formulas and asks, what is the structure of this chemical, which is presented in a linear compact structural chemical formula. To answer this, we do something similar to last time, and just draw out the formula and find which option it matches to, or at least eliminate options along the way. I'll draw a carbon at a time and a single line for the hydrogens to make it a bit faster to draw out. It's important to understand how to interpret these bracketed groups. It basically tells us that it is connected to the previous carbon as a side group, like a methyl group. So, drawing it out exactly as in the question, we've got what looks like a core of 4 carbons with groups coming off. Of course, there is a longer carbon chain hidden here, but first let's eliminate one of the options that is obviously not the answer. If we look at option D, it is a simple alkane with no branched chain groups attached, therefore this is not the answer. Coming back to our drawing, we see that the longest chain is 5 carbons, and we can start labeling the carbons from any end. Here we'll just label them as so. At this point we can eliminate option B, because it has more than 5 carbons as its longest chain. In this case it has 6 carbons. If we look closely now, you may already see that option A is the answer. But let's write out each carbon with the number of hydrogens attached based on our drawing. C1 has 3 hydrogens, C2 has no hydrogens, C3 has 2 hydrogens, C4 has 1 hydrogen, and C5 has 3 hydrogens. We can see on option C that it follows this pattern up to carbon 4, which has no hydrogens attached, whereas our drawing has 1. Therefore, option A is the answer, as it matches up exactly. On the next page, we continue to questions 10 and 11. Question 10 asks, which equation shows the hydrogen-carbon ion acting as a Bronsted-Lowry acid? By definition, a Bronsted-Lowry acid donates a hydrogen ion to another species. Therefore, if we want to show the hydrogen carbonate ion acting as an acid, it needs to appear on the left-hand side, and a hydrogen ion carbonate ion should be on the right-hand side, with something accepting the hydrogen. Going through the options, we see that D is not the answer, as in this case, the hydrogen carbonate accepts a hydrogen rather than donate one. Option C looks right, as the hydrogen carbonate donates to the ammonia to form the ammonium ion. Option B is wrong, as again the hydrogen carbonate accepts rather than donates the hydrogen here, and A could be right as well, as this is just the equation that we've written here. However, there is no base to accept that hydrogen, and therefore option C is the more correct answer here. On to question 11. Cyclohexanol is an alcohol and undergoes a dehydration reaction with sulfuric acid as shown. And we see that the product is missing. The question is, what is the major organic product of this reaction? Firstly, dehydration is the loss of water. We are dealing with cyclohexanol, effectively a cyclohexane ring with an OH group attached. This is an alcohol, and when alcohols, cyclic or not, are dehydrated, a double bond remains after the water molecule has been removed. Therefore, an alkene would form from this reaction. In this question, that means option B is the answer, as it's the only alkene. Okay, moving on to the next question, we have question 12. It asks, what isomer of C6H14 would have the fewest signals in carbon-13 NMR? We then have four options, all C6H14, and need to choose the one that has fewest signals. So carbon-13 NMR deals with carbon environments, so we'll be interested in finding the molecule with the fewest types of carbons in the molecule. When you have a symmetrical molecule, that leads to carbons with identical environments, and therefore less carbon environments. We can just go through these one by one to find the answer. In option A, the molecule is symmetric from either end. Therefore, if we label this side 1, then the other side is also 1. And then the next carbon from either side is the same, and so on. This gives us 3 carbon environments. In option B, a methyl group branches off the second carbon, which means we have 2 identical environments coming off of carbon number 2. But the rest are just unique environments with a different distance from that methyl branch. Therefore, we have 5 carbon environments here. In option C, we have 3 identical environments off the second carbon, as these are all effectively methyl groups. But again, the other carbons are unique, based on their distance from these methyl groups. In option D, we can start by labeling these 2 carbons as 1, and then the next one 2, similar to what we had in option B. But if we look from the other end, this is just a mirror image of the top left part of the molecule we just labeled. Therefore, we can say that these carbons are 1 and 2 respectively. In the end then, option D has only 2 carbon environments, and option C has 4. And we can say that option D must be our final answer. The next page has questions 13 and 14. In question 13, we have the decomposition of nitrosyl bromide according to the equation provided, and information on the amount and volume of the nitrosyl bromide at the start and the amount once it reaches equilibrium. The question asks, what are the concentrations at equilibrium of the 2 products from this decomposition, nitrogen monoxide and bromine gas? We can draw up an ICE table, which divides the situation into initial, change, and equilibrium with respect to the number of moles of each species in the reaction. Initial is the number of each at the start. From the question, we know we have 0.64 moles of nitrosyl bromide. We also know at equilibrium we have 0.46 moles. To calculate the change, we bring in our calculator and do 0.64 minus 0.46. To find the change was 0.18 moles, which we can now write in. This means that the 0.18 we see in the change row under the nitrosyl bromide represents the 2 in the stoichiometric ratio, and we can fill in the rest of the change row of the table with respect to that. Of course, we also need to add the plus or minus signs to indicate whether we lost or gained that number of moles. As we started with none of the products initially, these will be pluses, while the reactant is a minus. We can fill in the zeros for the initial moles of the products, and fill in that last row now as well. Therefore, at equilibrium, we have 0.18 moles of nitrogen monoxide and 0.09 moles of bromine gas, based on the stoichiometric ratio. As the question states that this all takes place in a 1 liter container, our equilibrium calculations are also the values for the concentration as well. Therefore, option A is our answer. Moving on to question 14, we have another equilibrium reaction, this time between nitrogen dioxide and dinitrogen tetraoxide with an equilibrium constant of 0.010. The question says, in an experiment, 100 cubic centimeters of nitrogen dioxide is placed in a syringe. The plunger is then pushed in until the volume is 50 cubic centimeters while maintaining a constant temperature. The system is then allowed to return to equilibrium. We then need to choose the statement that is true from the options. Firstly, in this situation we have 2 gases, nitrogen dioxide and dinitrogen tetraoxide. The left-hand side of the equation, the nitrogen dioxide, creates more molecules of gas when that side is favored, compared to shifts to the right hand side at a ratio of 2 to 1. The question says we initially have the nitrogen dioxide in 100 cubic centimeters. Before the plunger is pushed, we assume the system is at some equilibrium between nitrogen dioxide and dinitrogen tetroxide. Pushing the plunger in reduces the volume of the container, which increases the pressure. According to Le Chatelier's principle, we predict that the system will try to minimize that change. That is, it will try to decrease the pressure. Therefore, the side with less gas molecule production will be favored, and in this case, that is the forward reaction to make more dinitrogen tetroxide. Going through the options, option A is wrong, as the only factor that can affect the equilibrium constant is temperature. It is constant here. Option C is incorrect, as the dinitrogen tetroxide concentration will actually increase based on our reasoning using Le Chatelier's principle. Option D is also incorrect, as both gases cannot increase in concentration at the same time. Here we determine that nitrogen dioxide will go down, while dinitrogen tetroxide will go up. Therefore, coming back to option B, we can see that this is the correct answer. As the nitrogen dioxide numerator goes down and the dinitrogen tetroxide denominator goes up, this value will decrease. Going to the next page, we have questions 15 and 16. Question 15 asks us to find the concentration of an ammonia solution based on a conductivity plot. It states that we have a 25 ml sample of 0.1131 molar solution of HCl that is titrated against an aqueous ammonia solution. The conductivity of that solution is measured throughout the process, and we get the following plot. The first thing to note is that conductivity changes as the ion concentration of the solution changes, and the ion concentration changes as more hydrogen ion reacts with ammonia. The conductivity stops changing once adding additional ammonia doesn't change the ion concentration. That is, once the hydrogen ion concentration doesn't change. On this plot, we can see that happens here. This is at the 10 ml point, therefore telling us that 10 ml of ammonia solution was needed in order to titrate the 25 ml of 0.1131 molar HCl. Writing out the reaction, HCl will react with ammonia to form ammonium and chloride ions, all in a 1-to-1 ratio across the board. Therefore, we need equal numbers of each HCl and ammonia in order to completely react. We know from our formula sheet that N is equal to C times V, or concentration times volume, which we can calculate for HCl. Taking out our calculator, we can plug in the volume, 0.025 liters, and multiply it by the concentration, 0.1131, to obtain 0.002827 moles of HCl. Now, the number of moles of HCl that reacted is the same as the number of moles of ammonia, so we also know the number of moles of ammonia is 0.0028275. Using the formula for the concentration, C is equal to N on V, we can calculate the concentration of ammonia. Plugging in our values, we get as a final result 0.283 moles per liter, rounded to 3 sig figs as in the given options. This value is the same as option C, and therefore this is our answer for question 15. Question 16 asks us to determine which change would result in a high absorbance value in colorimetry. The situation we have is a blue copper sulfate solution and orange light of 630 nanometer wavelength, which is used in the procedure with a path length of 1 centimeter. First of all, colorimetry is based on the B-Lambert law, which states that the greater the concentration of the colored solute, the greater the absorbance of the complementary color. In this case, the orange light is complementary to the blue solution. At this point, we can already eliminate option C, as the blue light will not be absorbed at all. Blue being the color of the solution, which means the light is not being absorbed when it passes through, and why we can see it. Next, a higher intensity lamp will just mean more light passes through the solution. The solution itself will absorb just as much light as before, as the concentration and everything else is still the same. Therefore, option B is also incorrect. Also, dilating the solution will reduce the amount of copper sulfate per unit of volume, and therefore the solution will be less concentrated. This means less light will be absorbed. Because of this, we can also eliminate option A. Lastly, with a path length of 2 centimeters, the light needs to pass through a larger column or amount of copper sulfate to pass all the way through. Therefore, more light will be absorbed along the way, and option D is our answer here. The next page has questions 17 and 18. Question 17 asks us to consider a 2 gram sample of silver carbonate added to 100 ml of water in a beaker. The solubility of this carbonate at the given temperature is given as 1.2 times by 10 to the negative 4 moles per liter. This solution was then diluted by adding another 100 ml of water. The question is, what is the ratio of the concentration of silver ions in solution before and after dilution? Based on the options given in the question and the extremely small solubility figure, we can see the silver carbonate is not very soluble. What we need to do is consider the volume and moles before and after adding that additional 100 ml of water. So before, let's say we can get X moles of the silver carbonate to dissolve in 100 ml of water. This means that after, we get 2x moles of the silver carbonate to dissolve in 200 ml of water. This is because for the sparingly soluble solid, doubling the volume of water means we are doubling the amount of silver carbonate that will dissolve. To calculate the concentration, we just divide the moles by the volume. Before, this is x divided by 0.1 liters, while after, this is 2x divided by 0.2 liters, which simplifies back to x on 0.1 again. This means that the concentration is the same before and after, and therefore the ratio is 1:1, and option A is our answer. With question 18, we are provided information on a biopolymer for medical use and told that the optimal molecular weight is 2,900 plus minus 100 grams per mole. We are also provided a section of the biopolymer to see what it looks like structurally. The question is, which of the 4 options will produce the suitable biopolymer? Each option comes with a molar mass and number of units, which makes calculation a little easier. So firstly, we know our final product needs to be around 2,900 grams per mole. If we multiply the molar mass by the number of units, we will get the molecular weight of the biopolymer itself. Also, looking at the structure, we can eliminate options that don't lead to the section of the biopolymer shown in the question. Looking at that section, we can identify the repeating unit of the polymer by seeing where the pattern begins to repeat. This here is the repeating unit. Looking at options A and B, we can see a double bonded carbon atom in the structure. However, the only double bonded atom in the repeating unit above is the carbon-oxygen double bond. Therefore, we can eliminate options A and B as possible answers. This leaves us with 2 options that have the same monomer structure. However, we need to realize that this biopolymer is a condensation polymer, and each time the monomers join to form part of the chain, they will lose a water molecule. Therefore, we can subtract the mass of a water molecule from the molar mass of the monomer, 90 minus 18, to get 72 grams per mole, the mass of the repeating unit. Now we just need to know how many units are in the biopolymer, 32 or 40. Multiplying 72 by 32, we get 2,304, while multiplying 72 by 40, we get 2,880. Therefore, option D is our answer, as it lies precisely in the required 2,900 plus minus 100 range. On the next page, we have the last 2 questions in the multiple choice section, 19 and 20. Question 19 asks just to find the molar solubility of iron 2 hydroxide. With no other information provided, this must mean we need to use the information provided in the datasheet. That is, the KSP or solubility product value for iron 2 hydroxide. Looking back there, we can find the compound we are interested in, iron 2 hydroxide, and its KSP value of 4.87 times by 10 to the negative 17. Bringing this back to our question, the KSP is 4.87 times 10 to the negative 17. We link this piece of information with the equilibrium expression for the particular dissolution it describes, namely the reversible reaction of iron hydroxide solid dissolving to form iron and hydroxide ions in aqueous solution. So, that means the KSP is equal to the concentration of iron ions multiplied by the concentration of the hydroxide ions squared. If we let X equal to the number of moles of iron ions, then we produce 2x moles of hydroxide ions for every mole of iron ions, based on the equation we have written down. Assuming we have 1 mole of iron 2 hydroxide solid, let's say we place it in 1 liter of water. Based on what we said before, the iron ion concentration is X moles per liter, and hydroxide ion concentration is 2x moles per liter after it reaches equilibrium, where X represents the amount of the solid that dissolved. Plugging these values into our expression for KSP, we get X times 2X squared. This gives us 4X cubed. We know that the value, or KSP, is 4.8 times 10 to the negative 17. Therefore, solving for X, we have 4.87 times 10 to the negative 17 divided by 4, all of which is cube rooted. Plugging this in our calculator, we get 2.3 times 10 to the negative 6, and therefore option A is the answer. Moving to question 20, we yet again have a reversible reaction, but this time with a graph as well. The question states that cyanidin is a plant pigment that may be used as a pH indicator. It has 4 levels of protonation, each with a different color, represented by these equilibria. So in this end, we have H3Cy+, which is a red color, and when it loses a proton or hydrogen ion, it becomes H2Cy, which is colorless. When this loses a proton, it becomes HCy-, which is purple, and lastly, when this loses a proton, it becomes Cy2-, which is blue. All of this can go in the other direction as well, gaining protons. The question continues, saying the following graph shows the relative amount of each species present at different pH values. Along the y-axis, we have the relative amount from 0.0 to 1.0, and each curve represents one of the 4 cyanidin protonation levels above. We can see there is a complex relationship between them all, with a varying amount of each across the pH spectrum, which is along the x-axis. The ultimate question here is, what color would the indicator be if added to a 0.5 molar solution of hypoiodous acid, HIO, with a pKa value of 10.64, followed by the 4 options, red, colorless, purple, and blue. This question has a few parts, and we'll need to join together a couple of concepts. Firstly, the main point of this question is to find the pH of the final solution in order to determine the color of the solution of the hypoiodous acid. We are told the pKa value for this acid is 10.64, and we know that pKa is equal to the negative log base 10 of the Ka value. The Ka is the acid dissociation constant and equilibrium constant. Therefore, we can write out the reversible reaction this is associated with, namely HIO forming the hydrogen ion and IO- ion. This allows us to write the full expression for the equilibrium constant, that is Ka is equal to the concentration of the hydrogen ions multiplied by the concentration of the IO- ions divided by the concentration of the hypoiodous acid molecules. We know that the concentration of the hypoiodous acid is initially 0.75 moles per liter, as given in the question. Assuming this is a very weak acid, this will remain true at equilibrium as well. If we set the hydrogen ion concentration as X, then the IO- concentration will also be X, as equal numbers of each ion are produced when the solid dissociates. Therefore, we can plug in our values into the expression to get X squared divided by 0.75. Now, returning to our expression for the pKa value, we can determine the Ka value by rearranging the equation to make Ka the subject. That is, Ka is equal to 10 to the power of negative the pKa value. Plugging this in our calculator, we get 2.29 times 10 to the power of negative 11. We can now use the Ka value, specifically the numerical value, and plug it back in to what we've got down here. Taking this down to solve, we can say X squared is equal to 2.29 times 10 to the negative 11 multiplied by 0.75. Therefore, X is equal to the square root of 1.71815 times 10 to the negative 11, which gives us 4.145 times 10 to the negative 6. This is our hydrogen ion concentration. To find the pH, we can take the negative log base 10 of this value. This comes from the formula for pH, which states that the pH is equal to the negative log base 10 of the hydrogen ion concentration. Plugging this into our calculator, we get 5.382, which, if we look back at our graph, means that we are pretty close to the peak of the HCy- curve. At this pH, we see there is 0 H3Cy+, no Cy2- either, and although some H2Cy is present, it is colorless, so in the end, the solution will just be purple. This means from our possible choices, option C, purple, is the answer. This brings us to the end of the multiple choice section, as the next page is the start of the short answer portion of the exam. This is also the end of this video. As I said at the start, this is the first time I have gone through the entire multiple choice section all at once, and is in a handwritten style. Please let me know if you found this useful or prefer the older, neater slide style of going through the exam questions. Also, if you have any other comments or questions, please leave them below. It helps me make these videos better. Thanks for watching and see you next time.